Now we're going to do our second presentation, Schema Management with Scalameta, by Lars. Welcome, Lars, and thank you very much for coming here.
Thank you.
Yeah.
Thank you. Hi, everyone. I'm Lars. You heard I run a small company named Scling. We do data engineering, and I was going to, as Magnus said, I was going to hold this presentation like three and a half years ago. I was going to hold it at this meetup, and then at the Data Innovation Summit back in 2020. What happened then was the pandemic, and the Data Innovation Summit went online instead, and I held another presentation because I got so upset with the poor handling of data and data management during the pandemic. In fact, it was so poor that it killed people. Not in Sweden, but in Britain, it actually killed people by mismanagement of data. So that was the topic that I chose instead. And this presentation has been brewing for about 3 years, and is now finally going live after some laying still. What got me into data is a couple of events during my career. The first one was when I left academia to join Google, and I didn't work with data at Google at the time. But I learned 2 things at Google, or I learned many things, but most importantly 2. One was productivity, and I worked in productivity engineering, and I realized how much you can achieve if you run in circles around your competitors. And Google had the absolute best productivity tooling and processes at the time, and still have. So that was a great education. And the other thing that I learned was how much value you can get out of your data. This was back in 2007. Google was the only company at the time doing what later became known as big data. So that's how I steered my career. After a few years, I realized that Spotify were doing interesting things in the area, and that's how I learned. That's where I learned the craft of data engineering. Built out one generation of Spotify's data platform, the one that sort of managed to democratize the use of data within the company. I've continued as an independent consultant for a while, and with a bunch of companies, and nowadays I run this data engineering startup. I'll describe a bit later what we do. But first I'd like to get to know you as well. So I will speak about some of the things we do with Scala. And I wonder how many people use Scala here or know Scala? Okay, half of you. Some of the examples might be difficult to understand if you don't know the syntax, but I promise you it will be less difficult to understand than the previous presentation and understanding what Agda is up to. The second question, how many people here dabble with data, like in data engineering, data science, analytics, and so forth? Okay, very few. Okay. Then I will keep those things at a fairly high level, as much as I can. And I'd like to start at that high level to explain what we do and why, and then in that context I will take you all the way down to very gory technical details, so there will be a little bit of for everyone. But I want to explain the context that we do, that we operate in to explain some of the choices that we've made. All of the things that we humans do, the value creation that humans do, go through sort of phases where we start with doing things in a very manual level, cook over an open fire or transport things with a cart and horse and so forth. And then we get tools that we can hold in our hands and steer like a car. Or a stove or a chainsaw, and we become more powerful, but we still steer it with our hands. And from there it goes on to an industrial level where we as humans don't really participate as much. We just control the process and change the process and work with the process, but the process itself is mostly automated. And we have gone through these stages with the software engineering and various other technologies and with data. So the manual of data is like pocket calculators or Excel, and most companies are here in the sort of the database and data warehouse age, of data, whereas a tiny fraction of companies, and Google was the first one to break through this barrier, have gone into an industrial age of data, where they work with the processes instead. This is Spotify's flow of data from 10 years ago. And in most companies, the flow of data like fits here. So these are orders of magnitude bigger. The difference between working with as a craft versus as an industry, as I said, is that humans in the artisanal way of working, humans control the processes. And the components that you use are sort of convenient and easy to use, easy to hold. Like whereas an industrial robot, for example, is very difficult for a human to steer. It's just not made for that. And likewise, it's likewise the case with our software engineering tools and our data tools and so forth. So what happened in the sort of data evolution here is that the jump here from the artisanal stage where the data warehouse and sort of semi-automatic processes was the state of the art to this stage it was enabled by the most successful cargo culting ever, which is Hadoop. When Doug Cutting and another person whose name I've forgotten looked at what Google did and did an open source implementation doing exactly the same thing. And that spread among the Silicon Valley companies and outside of Silicon Valley after a while as well. And because of the limitations of Hadoop, people were forced to work in a different way. And that pushed some of the companies into these processes instead of the manual steering. Now, this got very hyped and really cool about 10 years ago, and all of the big companies wanted to do that as well. So if we just install a Hadoop cluster or a Spark cluster, everything will be fine, and we will get magic, and we pour all of our data in a data lake, and great things will happen. That didn't turn out so well. Most of them completely failed. There are some spectacular failures here in Sweden as well, when tons and tons of money were burned. And the conclusion was that, no, we can't do this. We go back to the sort of the old ways of working and get better data warehouses. We buy Snowflake instead, or some of the newer tools that are still sort of the same as before, but a little better. We've seen this pattern before. Back in the 90s, building programs became really, really popular. And there was a huge demand, but things like C++ and Smalltalk and Java and all of the other sort of third generation languages were sort of quite difficult to use. You needed a software engineering education. So people came up with simpler ways of building programs, right? Graphical ways, UML, you can drag and drop things, and programming should be for everyone. These are completely extinct today. There's not a single significant program written in 4GL languages. What instead happened was that we educated people. And now software programming is the most common profession in Stockholm. So what has happened now is that we have entered the 4GL stage of data engineering, basically, with tons and tons of tools that pop up and enable everybody to use graphical tools and low-code tools and no-code tools to do data engineering. And in fact, one of these is from the 90s, a 4GL tool, and the other one is Apache NiFi. They sort of look almost the same still today. Now, I may sound like I'm mocking them. I'm not. These serve a purpose, right? Because we're not here yet. We don't have the competence. So these have a value for a period of time, but we will eventually move away from them. So what does it matter to do things industrially? It's not, I mean, there's no self value in having an automated process versus a manual process that has to be translated into some kind of business value in order to be valuable. I call these sort of the platforms that we work with data factories, because they are similar to manufacturing factories. And if you look at a real factory, you can say that every time you move an industrial robot moves, some kind of value has to be generated, right? as a proxy, but because otherwise it wouldn't move, right? It's maybe drilling one screw or one hole or one screw doesn't amount to value, but the value that spits out of the factories is some way proportional to the amount of things that happen in the factory, right? So you can say that if someone has a factory and 1,000 things happen per day, and another company has a factory where 1 million things happen per day, that million thing probably produces more value. And if you translate that to working with data, what we do in these factories is usually we work in batch processes, and the batch processes produce data sets. Some of these data sets are intermediate, but some have sort of an end value. This could be showing on a graph how many users we have, or the trends from yesterday, or recounting new recommendations for all our users, or calculating a new index for fraud detection or whatever. So if we count the number of data sets, we get some kind of hunch of where companies are in terms of maturity. And if you go to the traditional enterprises, the banks and the insurance companies and retail and so forth, they usually have these like BI teams with from 10 to 100 people. And from talking to lots of these companies, I deduce that they usually produce about on the orders of hundreds or maybe in the low thousands of data sets per day for the really big banks. When I started at Spotify 10 years ago now, we were producing somewhere around 20,000 per day. In 2017, they came public with some figures, and you could deduce that they were now at the order of hundreds of thousands per day, and there are probably, if you extrapolate, in the millions now. 2016, Google published that they were producing 1.6 billion data sets per day. And if you start thinking, well, okay, why would you produce so many data sets? How many relevant things do we have? We have the users, we have the sales report, you can probably come up with a few hundreds. Clearly, they are soon doing something radically different. The radically different is that they have moved away from the sort of the traditional value of data, which is analytics, reports, understanding your users, and so forth, out into the land of where data plays a much more significant role in the product. They sort of shape the product, they shape the logic, and all of the sort of modern AI and machine learning are out here on the fat tail. And the volume of this fat tail is large. So if you can push the cost of working with data down, you can get out here and you can have disruptive value. So what we do is to run these factories as a service. That's sort of our business model. And we don't do with what you today see as the modern data trends with the data constructs and the modern data stack and so forth. We're completely doing sort of old school big data. I will not go into details about what we're doing because this is not a sales presentation. We have a very simple marketing strategy. We share information freely that we believe will be useful. So I'm here to share some of the technical details with you of how we work. And I will say many times, we do X and we do Y. I want you to interpret this not as we do all of these fantastic things, therefore you should buy our product, but we do all of these things, and maybe some of these are useful for you. Maybe you can learn from them as well. There are a number of things that differ between success and failure here when working with data factories. Some of these fall into the organizational realm, how you form teams, how you collaborate between teams. The big revolution of big data was actually not technology. It was a new way of collaborating between the teams, where the data lake is the central thing, where you pour all the data and you make it accessible and to everyone and easy to innovate and so forth. If you read this book, it sort of describes the way that modern IT companies, the successful modern IT companies, organize most of them. The other factors here that I mentioned are ways to work with technology. and it can be summed up as modern software engineering processes. This is another epic book that sort of sums up these practices and processes as well. Building on existing, well-known, well-established software engineering processes that we know are efficient is crucial to success with data factories. But it's not so common when working with data. It might, if you don't work with data, but in regular software engineering, it might be obvious to you. It's not obvious in the data realm. So I've been talking a lot about factories. What are they? They are essentially taking the old traditional way of working with data in databases where the sort of the entities, the records, are mutable, which is in a way an object-oriented way of working with data. You have these tables with records and you mutate them, change the state and so forth. Taking that and going to a functional paradigm where you say that we have raw data here that we either take facts as events or in some cases dumps of the databases out there. We store them essentially forever. I promised to go into privacy as well, and store forever doesn't go so well with privacy, but bear with me for a while. We have a simplified model for now. We store these things forever in raw form without any processing whatsoever. And then we refine the data and create valuable things out here to feed our services and to feed our analytics by step transforming these things. So we do this at an architectural level, right? But this is essentially functional programming, turn into architecture. And this is what Hadoop forced us to do. We didn't understand this when it happened. But because it couldn't do indexing, it couldn't do transactions, so you couldn't change things, so we were forced to do like sort of MapReduce steps and implement the business logic as functional transformation. And therefore, we were, since we couldn't do transactions or anything, we were forced to make these data sets immutable. And it turned out when we made them immutable, anybody could read them without disrupting our own service. Whereas if you go and bang here, you disrupt the operations of the service and you don't know how it changes and so forth. But since these are immutable, anybody could use them. And I discovered at some point that a data set that we produced were used by 200 different use cases downstream without us knowing it. So that's a great example of sort of minimizing friction to creating business value, because each of those 200 created some business value for the company, and without synchronization between the teams, which is usually the bottleneck. Schema management. All of this data has some kind of schema. The schema defines the structure of the data. And in some cases, in relational databases, these are very hardwired. You explicitly have a schema for a table, and the relations between them are stored in the database as well. Whereas we don't work so much with databases, we work with file storage, and then the relations between the data sets are sort of implicit in code rather than expressed in the storage. Somehow we need to define these schemas, and there are a bunch of different strategies. One of the popular ones is to use Avro definitions. Avro is a serialization format suitable for data storage. If you've used, some of you might have used protobufs or thrift or whatever, it's similar, except that with Avro, the schema is actually stored with the data, which turns out to be a lot more convenient when working with data storage. I've seen all of these in some form or another. So you can choose either to have sort of specific formats or have code as the way to define your schemas. We use Avro as our serialization format. For various reasons. It has a couple of different variants. You can either store it binary, in which case it's very compact, or store it more verbose as JSON. Either way, you need to have some kind of code to sort of serialize and deserialize again. And when you store it in files, the schema is attached to the binary record, so that tools that read data can also find the schema and understand the data. There are two main strategies for sort of keeping schemas in consistency. One is called schema on write, in which case there is when data is produced and put in storage, there is a clear definition on what the schema of that particular data should be like. If you're used to relational databases, this is what all relational databases use. In the case of relational databases, there's a check as well. So if you try to write something invalid, it will technically fail and you will get an exception. You can do schema on write, but without technical checks, and then it's sort of more of a social convention that if you wrote the wrong thing, you're a bad person. So schema on write is a sort of represents a philosophy of strictly checking what data ends up in the storage. The opposite is schema on read, where we might store a little bit of everything, but then as we use it, there is of course an expectation of what we are supposed to find there. And in that case, we sort of check when we read things that all of the fields that we read out are present, or otherwise we will get some kind of exception or problem because we don't have the data that we need. There is an interesting property here, is that if we change the schema that we write down with schema on read, when we sort of join things or copy things, the new fields will sort of flow along, right? Whereas in a schema on write situation, which is typical for data warehouse environment, we need to change the schema in all of the tables where we propagate the data. And the strict and loose typing is similar, but not the same, as the philosophies of static and dynamic typing, like in languages. Because in static typing, these are the fields that are supposed to be in the record or in the class. Whereas with dynamic typing, we can accept a little bit of everything, and we don't, if there are some extra, we don't care, they just float along. We, in order to sort of read and write code, we sometimes decide to generate code, and then if these two go better together and these two go better together, but we can also sort of cross-pollinate a little bit and sometimes do. The effects that fields that we add out here in the source propagate through the systems, through the pipelines, through the steps of batch computations out here to where we need them, is very handy for analytics purposes. Because then you can ask the people in that handle the mobile client to say, oh, can't you just add a field for like screen resolution or whatever? That would be really useful to know. And then suddenly it pops up here, without having to synchronize with all of the teams in between. Remember, synchronizing between teams is usually the bottleneck. But the drawback of this is that if you make a little typo out here somewhere and you get it wrong, then much later you notice the problems, which if you don't feed analytics but feed real world applications, this might not be the desirable trade-off. This is one of the oldest slides that I have. It's like 10 years old or something, but it sort of still holds. Since I made this slide, this has shrunk, and schema on read has become a lot more popular in data pipeline applications. There is also questions of compatibility. If you mostly work with APIs and microservices, you also have schemas there, but and then if you upgrade, you need to think about the compatibility if you have an old client and a new server, or the other way around, right? That compatibility problem becomes much more significant if you work with data, because with microservices, once everybody has upgraded, you're all on the new version and you can forget about the old. Whereas if you store data, you can store for years and you have all of these old old schema versions hanging around. So you have to have some kind of strategy. And when changes cannot be made either forward or backwards compatible, you have to have a strategy for sort of incompatible changes. And there are a couple of different, what we usually do with our clients is to just recompute everything, which works because our clients don't have huge amounts of data. If you have sort of web scale data, this is not so convenient, so you'd pick one of the other strategies. This is also a very, very old slide. This was made back in the days when all of the big data innovation happened on the JVM. Nowadays, Python is completely dominating, or mostly dominating at least. The reason that Scala bubbled up in this world is that it connects sort of to good properties from two worlds. One is the JVM world where you have the static typing and you have good operations tooling and so forth. But if you put data scientists and say you now need to go and do your prototyping in Java, they will go find another job because of all of the boilerplate and so forth involved. So we found that sort of Scala was a common ground where these two kinds of philosophies could meet and actively work well together. And that's why some of the popular big data tools were made in Scala. So zooming in now onto Scalameta, which is a tool that we use for parsing Scala source code. Scalameta is a parsing tool that parses code, and then you get a representation of the code that you can manipulate and either write down again or do something completely different. There are a couple of levels when you're parsing code. One is the tokenization or the lexing, where you take this and you split it into words, basically. And then from those words, a syntax tree, an abstract syntax tree is formed that represents the code, but doesn't understand which types are actually which. It just knows them sort of by name. And then there's a step of semantic analysis where these names are resolved to actual types. Right? Scala, if you have a C preprocessor, it works at this level. Scalameta somehow works at all three of them, but mostly on this level, and this is where we are going to be working today. There are a couple of use cases of Scalameta. One is formatting, which is where it needs all of the little nitty-gritty tokens as well. There's a code formatting tool called Scala Format. There is a tool called Scala Fix for static analysis of code. So it can give you warnings, tell you if you have unsecure code or whatever. Scalameta is nowadays also used as the macro implementation in Scala 3, which is I call online code generation. It's dynamically generating code while you are compiling. What we use it for, which we'll see, is offline code generation. So during the build process, we read the source trees and generate code. It says code transformation here. This is a quite cool application of meta programming or of Scala Meta. This example is from a file in the Shio library. It's a data processing library from Spotify that you can use if you're upgrading happen to be upgrading from 0.7 to 0.8, then this is a transformation rule. So if you apply this to your source code with Scala Fix, it will change all of these calls to this function to another name instead. So that's a very sort of automated approach of upgrading libraries that I haven't seen in any other language. So what you get when you ask Scalameta to parse the code is a syntax tree, and this code here, which we will see examples of later, translates into sort of this tree. This is not Scala syntax. This is what you get if you say please print the tree on the screen. And you can see sort of the structures here are represented by structures here, and you can sort of deduce that yes, we can probably go around and program our way and navigate this tree. It can be a little bit difficult to realize, the match between these when you're programming. So there are a couple of cool tools in Scalameta. One is called Quasiquotes, which basically, instead of saying, here, I have a piece of Scala here, can you please parse it and give me the tree? You apply this little quote here. And this is a macro that actually also type checks, right? So it reads this and it makes it the right type. So you get a compile error here if you have a syntax problem inside here, which is a bit odd but cool. That confused me when I first used it. You can use quasi-quotes the other way around, so you can use them similar to the way that you used regex matching in Scala. I don't have an example of the regexes, but when you do regex matching in Scala, you have this match in case statement, and then you have this regex, and you can have some groups here, and you can pick out the data from those groups. So you have the same type of matching and says, hey, does my source code match this pattern, or this source code pattern? If then, yes, please give me those pieces like the A here and the B here, and so forth, and give them to me as variables with the right type, of course, so that I can work with them. So, schema definitions, back again. What we have decided to use is to use Scala case classes as our schema. So for those not familiar with Scala, a case class is a dumb record in a way. I think they're called records in Java. It's similar to data classes in Python. So they are used for sort of transparent, simple records of data with a number of fields and so forth. You get a lot of syntactic convenience, so they are very attractive to use in Scala. And then we use, as I said before, Avro for our sort of serialization format. From these case classes, we generate a whole bunch of different things to help us with the management of schema in different parts of our ecosystem. And when I did this presentation 3 years ago, we only had this one, so it has now grown a bit. And I will briefly go through all of these to give you examples here. So one is the Avro codec, and you'd think that Avro, being a very popular format, you could just take a case class as record and say to Scala, please save it as Avro. And that we tried that for a while, but the libraries are not really good enough, so they mishandle some cases. The Java libraries are better. So what we do is we generate Avro definitions, which look like this, from our case class definitions, and then we ask the Avro tooling to generate the Java serialization code. And then we don't want to be in Java land because Scala is a significantly much better language for data processing. So we generate converters that in the IO routine almost immediately convert Java to Scala. You might think, oh, how about performance? We don't care. There are 3 dimensions of performance that are relevant. The one here is that you might think about is runtime performance. That's mostly irrelevant to us because most of our clients have small amounts of data. The performance that we care about instead is developer performance, the ability to quickly iterate through new things, and that's much more important. And the other one is test case performance, so if the tests run quickly so that we can iterate quickly. So the evolution of code is much more important to us than the actual data execution. And this is an example of code where we generate these converters. And now you see the quasi-quotes shine here, because instead of building this huge construct tree, we can sort of program Scala within a string and inject all of these different sort of template variables to form Scala code. And if we get this wrong, we get a compile time error. In some cases, we receive data CSV, and there's a fairly good Scala library called Kantan CSV. It needs some help a bit here and there to sort of interpret headers where it sometimes gets a bit confused. So we generate some of the helpers and codecs that are sort of case class specific as well. When we test code, we usually run data processing jobs and say, here's the input data, run the job. Here's the output data. Compare the output data either with a known fact, what it should be. Sort of if you produce 10 records, here are the 10 records that you should see, or we just look at bits and pieces. And one of the problems we had before is that if any of these records contained floating points, you would have an exact floating point match if you just compared one record to another. That leads to very spurious errors when you differ in the decimals. So we use type classes called record equality here to say that, okay, two records are defined as equal. If they all match, but for the doubles, you can allow a little bit of leeway here so that you don't get confused. And for those not familiar with type classes is basically a way of saying, hey, to the compiler, hey, if you have this class, which somebody else defined, and would like to do a certain operation, I know how to do that. It's commonly used, for example, for sorting. So if you have IPv4 addresses and say, and need to sort them, you can say, hey, here's how to sort the IPv4 addresses, and then the sorting libraries work and so forth. We use Scala for all of our business logic. We use Python for glue code, and Python in some cases when there are attractive Python libraries, which happens with some machine learning cases, for example. So we need to bridge between Scala and Python. We still have the definitions in Scala. And since Python is dynamic, it can directly read the Avro definitions and say, okay, I now understand the structure of this data. We've taken this a step further, and from Python also defined the type or the schemas when we store these records in relational databases, which we use not for computation, but for making things accessible to the user. Or to applications. And you might wonder why we do that in Python. The reason is that the Python workflow orchestration, which we use to keep things together, is kind of the piece of software that owns the definition of the MySQL tables. So we can annotate, we use annotations here which propagate through the Avro definitions and go on and then go out into MySQL. What we used to do was this, in sort of explicitly define the same kind of schema as we would have there, but this is of course error prone because there's duplication between the definitions, and this took a lot of toil, took a lot of effort to keep these things in sync, and it's easy to make mistakes. We also use the fact that Scala and case classes is a stronger or has more expressiveness than the other alternatives for storing schemas. You remember we could store it as Avro definitions, we could store it as JSON schema and so forth. In those cases, you are limited to very few types. Scala has a very strong type system. So we use something called logical types, which basically says that from a semantic perspective, I have this one type, but when you store it on disk, you can store it as an integer or string or one of the basic types. And Avro has a little bit of support here. For example, it stores dates as integers with days since the epoch, and timestamps as long since the epoch. And there's a little quirk here that's caused us a lot of pain, which is that the default storage of timestamps in Avro is millis since the epoch as long. And millis, as you might realize is not always sufficient granularity, right? In computer system, things happen more like in microseconds. So if you have microsecond resolution, you can usually order most events, but millisecond resolution is not enough to order events in computer systems. So we prefer to store things as microseconds, but and that has caused a bunch of trouble with various Avro libraries. And at some point, I scratched my head and said, why did they choose millis? It's probably because Java chose a system current time millis, but why did Java use that? The only reason that I can think of is if you store dates way beyond the year of 294,000 something, then, or timestamps beyond that time, because that's when it matters to have millis and not micros. So I have a conspiracy theory that some time traveler had a Y2K problem, right, in this year and came back here to fix it, and that's why we are suffering. Anyway, we have our own logical types that we sort of define, and you could think of very simple ones, such as there's no concept of set, for example, in Avro, so you could store set as a list, and then read it up and assert that all of the items are unique, and when you get up to the case class, it's a set, so you have all of the semantics. You can have not only primitive times, but time intervals and so forth. And these are some examples, like year, month is something that we use a lot, but it has no Avro representation, so we say, okay, we just store it as an int, and then there's some other code that translates between them. And I said physical on the previous slide. This is something that we haven't had the time to dive into yet, but we had a production issue recently where we mixed up fields that had kilowatts and fields that stored kilowatt hours and tried to add them or compare them or something. And that obviously didn't work. And you know, these are different types. Semantically speaking, right? And we have a great type system, so it should be a compile time error. And I used to grow up with C++, and there was this amazing library called Boost Units, which I never had the chance to use, which essentially concluded that all of the SI defined physical entities are actually 7 different dimensions. There's like mass, and there's length, and there's time, and there's energy and candela and whatever. So it had this powerful template library that would keep these apart, and if you multiply or if you divided length with time, you would get speed, and it would keep track of all of the types and so forth. And you can't do this in so many languages, at least not with static typing, but there is an odd Scala library called Coulomb that does this. I don't think it's possible to do with Java, but Scala has sort of sufficient strong type system. It's just one guy developed this Coulomb. So we're looking forward to sort of generate different types for kilowatts and kilowatt hours and store them as doubles on disk, and then as we read them up, get the right types and so forth. But we're not there yet. So going into privacy. The way that we work with preserving privacy here in the lake is to separate the sort of the personal data from non-personal data and treat them slightly differently. The things that are challenging in terms of sort of GDPR regulations to cope with in a data lake is the right to be forgotten, and then to have limited retention. Because if you have all of these data sets and the data is copied and it's immutable, and someone says, hey, please forget me, forget all the things that you know about me, this can be quite expensive to do something about, and it sort of breaks the whole sort of structure that we have. So we use something that I named the lost key pattern long ago, and it seemed to have stuck. It uses crypto threading. So for every record here, if you have some gray non-personal data, some red personal data, you take the personal data and you encrypt it with an encryption key. And you store these encryption keys in another table or in another data set. And this is kind of mutable in the sense that you don't actually mutate it, but you add new and new keys as new users arrive. And every once in a while, you take the request that of people that have been that should be forgotten, and you remove their keys. So the data, personal data, is still floating around here encrypted, but you have forgotten about the key, so you can no longer use it. Not everybody uses this pattern, but a couple of companies do. For example, Spotify. So it has worked fairly well so far. One of the benefits is that you can pass this encrypted data around without any privacy issues. So some of the intermediate steps might not even know what the data is, and then only later, if you need it, you can decrypt it. This is a bit tricky to program these things. So we have a structure that we call Shieldformation, where we generate sort of derivative schemas and also jobs to transfer between them. So if this is the main schema here with the personal data, in this case, some kind of sale transaction with an ID that defines the human, sort of a customer club ID in this case, and the store ID, which is personal data, because if you know the store ID, then you know where people have been, and that's very much personal data. And then some non-personal data, like what was bought and when was it bought and so forth. What we do is to generate the classes, the corresponding classes where the personal data has been encrypted, plus a shield ID, and the shield is where the encryption keys are stored. And then you also generate an anonymous version where just all of the personal data has been dropped. And this is useful for a number of use cases. And the GDPR mandates that if you have use cases where you don't need the personal data, you're supposed to drop it sort of as quickly as possible. So this matches well to those requirements. And then we generate jobs that translate between these. So because this is all sort of boilerplate, there are lots of similar jobs that just differ by the schemas. It says Spark job here. We actually ditched Spark a few months ago and we don't use it anymore, but you get the point. It's a batch job in some kind of data DSL language. And then the sort of flow is like this. Like if you get your sales in here, as data comes in, you generate these shields for all of the new user IDs that you see. You encrypt them here into this shielded job, and that's the one that you keep around forever. Whereas the shields, you append new users and you delete the ones that want to be forgotten. And since you do it there, this means that you can now keep this forever, and the whole, apart from this little shield, all of the sort of the model with immutability and so on works. If you need the personal data, you have an exposed job, and you can take it out to a system where it's stored in clear text, given that you do precautions here. And in many cases, you can just sort of have jobs that drop the personal data. And the precautions that I mentioned is that you need to secure the systems more ambitiously if you have personal data in the systems, basically. There are a couple of different ways of or strategies of partitioning personal and non-personal data, and these are the sort of the general patterns that I've seen. In some cases, I've seen people try to sort of scramble the data as it comes in and sort of not store all of the data. So, and then hopefully you can use some of it. This doesn't work, and it's not so common anymore. In larger enterprises, it's common to see that you store a bunch of data, and then when you access the data, you apply lots of tight rules to see, does this user, does this application really have access to that kind of data? This is probably the most common solution out there. What we do is what I call a locked lake, where we store all of the personal data in the lake. In our case, both the shields and the personal encrypted data. In some variants of this, you store the shields outside if you want tighter security requirements on the encryption keys. But no humans have access here. So in order to do something, you need to sort of spit it out to another system where you have different access rules, and where in the case of personal data, only the people with that actually want the actually need to access the data can access the data. This scales to a certain degree. For very large organizations, it doesn't scale anymore. So the largest organizations have this kind of setup, but federated in different cells, maintained and governed by different teams. So if we apply that to that locked lake model to the what the Shieldformation does, this is what's in the lake, where only machines can see it, no humans. If we expose something for a particular system that a particular team needs to see, they sort of own the governance here, and then there's usually some kind of green area without any personal data where it's completely democratized and anyone can access it. And in order for this to work and data to still be democratized and so that everybody can innovate, it's important that anyone can create jobs and deploy flows that work on this data, which is something different than for a human to access it. So that's permitted within the regulations. So with all of this schema generation from our case classes, what we've essentially covered is to get the best of both worlds with sort of schema on read and schema on write, while still being in the schema on write strictly checked world. So we know if we, for the part that we control at least, which is out to our clients, if we change something over here where the data is generated, since we generate everything, it will ripple through all the way out into the analytical databases. So we no longer need schema on read, basically. Back to this again. What I've presented to you here is a couple of things in which we sort of perform these steps, right? These are guardrails where we generate schemas to keep things in sync, to help with the testing and so forth, and to minimize operational toil by keeping the MySQL schemas in sync with the Scala job schemas and so forth. So these are steps that we take to sort of strengthen the software engineering processes in data engineering. And if you look at some of the trends out there in working with data, for example, the no-code and low-code, or the measure or data measure, data contract, they essentially makes lots of these aspects more difficult. So we are clearly, the pendulum has swung way away from the industrial ways of working. The more blog posts you read, the further away you will get from what the sort of the data elite does. I have a little history of working with different types of companies. I was employed at Schibsted for a while, and we tried to do this huge effort and burned a gazillion Norwegian crowns. It was a very bombastic effort. It eventually, some interesting things rose out of the ashes, but it basically collapsed under its own weight. But now they are doing really well. I was at a large bank for a while, and this is not unique for that bank, but I've seen several banks spend about 2 years going from the decision we should have a data platform and the data lake to actually getting the first flow out in production. One of them, the Dutch Rabobank, actually went on a conference presentation and said, we spent 2 years and now we have the first flow and we are very proud. And then they came back a year later. We now have 3 flows and we are very proud. I can't find that presentation anymore. They probably took it down. After seeing these huge efforts, some of them are close, some of them are at a distance. This is my last freelancing project. This was at Bonnier News, where I said, maybe we can skip all of these huge technical efforts and just be aligned with the use cases and try to get rid of as much technology as possible, focus on stakeholders and use cases and see if we can get this industrial way of working without all of the technology. And this worked really well, and this is essentially what we have done since. So the things that I've shown you here today on killing the toil and removing friction and building on strong software engineering processes, they make a huge difference. From instead of spending hundreds of millions of crowns, we get up and running and build flows within weeks or months with 3 orders of magnitude less money. And if you compare these numbers and the number of data sets that we produce, we are not at Google level. We haven't done their investment, but we are at a similar level as Spotify in terms of number of data sets per employee or number of pipelines per employee, but without spending hundreds of person years in investment. That's roughly what I had to say. Questions?
Questions? They all want to go on the data engineer course now.
Oh, yeah. Sorry, I used to do courses, but I don't do them anymore.
Bad luck. Not any questions, then I'll shoot some. How come you came into this? To data?
Well, that was the sort of the first slide. Yeah. I realized from my journey at Google that this is where the future points. One of the things you get at Google is a crystal ball. You can see what the future holds for other companies. So I was very lucky. I came in on a banana slip, basically. And that's what initiated my interest.
Cool. How come data engineers or data engineering is behind software engineering? How come software engineering is ahead? Is it technology? Is it culture? Is it something else?
Software engineering is an older technology. I mean, the term dates back from the Apollo program. I think it was coined in the 60s. If you look at other disciplines as well, these factories that I mentioned, you have these now in software engineering. I mean, it used to be the case when I started working that you'd build a program with you would type make my program or something. And if you go to my dad is also worked with computers. If you go to him and his colleagues, they wouldn't have make, right? They would type compiler, all the compiler flags, get an a.out file and use it. So when I started, we had these power tools called make and the compilers and so forth. But we have now, since then, shifted to factories, right? It used to be the case that we would make our program, SSH to the machines, install it, change a few config files, and okay, is it working, not working? Nobody does that anymore, right? We have a factory that, from the source code, creates a pristine container image built purely from source, and we don't ever mutate that image. Nobody does that. That would be madness, right? But we still think it's okay to mutate data, right? Even though we have reached this maturity in software engineering. So that has become a factory. And then you go to operations, right? Which is another field which is behind, is at about the same pace as data engineering, and you say, okay, I now have a blueprint in like Terraform or Pulumi, and that's okay, but how can I test it? No, you can't really test it because that's, cloud is not made that way, right? So you have this halfway, you have the power tools, but not fully industrialized. And then you go to security, and then even further behind, right? I think that 10, 20 years from now, we're going to think it's absurd to have these machines that run months after month after month. And if you get a breach, the attackers have a foothold in months or years. That's insane. Why don't we rebuild our machines all the time, right? Yep. Because we don't have a factory. Yep. I think it's the older the discipline, the more it has gone into evolved into factory, and also building factories for all of these data and ops and security is completely dependent on software engineering. That's how you build the factories.
Yep. How much data growth do you get in your solution? Because if you don't mutate data, do you throw data or do you?
What I skipped over a bit briefly is that the raw data that we keep forever, but the derived data we can always rebuild. So that has we have a sort of a retention, a lifetime retention window, which is dependent on the use case.
Of course. Anyone else? Yeah. We have a question in the crowd.
Where is most of the data that's being collected? Where is it kept physically?
In the heathen days, it used to be in Hadoop clusters, in the sort of the early data factories, and that would be on-prem installations. If you go to the banks, insurance companies, and similar, they are still to a large degree on-prem and still use Hadoop. For the rest of us, we have moved into the cloud. So it's stored in like S3 buckets, Google Cloud Storage buckets. That's the sort of the main lake storage, and then we use sort of managed databases when we need indexes.
Is there like a physical facility or something where this data is actually kept?
If it's on-prem, then either some sort of large enterprises actually have their own data centers. I mean, the bank where I used to freelance, they had these big mainframes in the basement of the building, basically, and all of these diesel power. That's very rare. I think Kiva here, I think is in a way on-prem, but I would guess that they don't have their own data center, but rather rent someone else's, rent space or rent machine in someone else's data center. And then it depends on where it is. Some want to be on Swedish soil. If you're in the clouds, that's usually an American cloud, and then you're rarely, sometimes on Swedish soil, but most often not. That's the thing with the cloud. You don't no longer care where it is.
You try to not care.
Something like that, yeah.
I was thinking, which library do you recommend to data analytics in Scala?
Within Scala, Spark is the most popular, so that's a reasonable way to start. We left Spark for reasons, but that's a good starting point.
I have one more question. If you're a data engineer, now you realize you have to learn how to make a factory. Where do you go? You go to Google, or you Google data engineer?
No, you need. If you actually want to learn, you need to work at a place that has a data factory. So that's the only efficient school, because you need to get in there, get your hands dirty, and be there. And I have.
Can you recommend some places?
Sorry, let me just finish last sentence. I have taught a lot of people that came into our team, and they teach them. And if they are senior software engineers or senior like BI developers, depending on which direction they come from, it usually takes about 6 months until they can teach the next person. And given that is in a well-functioning factory environment, right? If you're outside that, then that time stretches to infinity. So you have to be in such an environment in order to learn it well. In Scandinavia, the most mature company is Spotify, by far. Then there is Klarna, King, Schibsted, Maersk. I believe that Goldman Sachs has some interesting activities here in Scandinavia, but they are not so open with what they're doing. Nope. So there are a few of these companies. We did some progress at Bonnier News as well. So that's where you learn it.
Hmm.
The problem is that they are so few. So the knowledge, it's different in the US because they have been doing this in such a scale and for so long in Silicon Valley that it has spread much more to other companies. And that's why we are trying to figure out another way of collaborating so that we can bring this to companies that cannot attract the talent, the necessary talent, a critical mass of necessary talent.
Okay. Thank you very much. Again, yeah. Thank you, Lars, and thank you everyone for coming, and thanks again, Kivra, for hosting us here in a nice venue and very nice food. So that's it for the evening, and with that said, have a nice evening in the live chat, and everyone here, enjoy the rest of the food and drinks and everything. Yeah, thank you.